In the last video, we talked about Maclaurin polynomials, which was developing a polynomial centered around x equals 0 that would approximate a given function centered at x equals 0. And as the degree of the polynomial increases, we were able to find a polynomial that approximated the curve for a better and longer interval the higher the degree. Now, as I said, the Maclaurin polynomial idea that we've developed was centering our starting point around x equals 0. But we may actually want to center our polynomial around a different point. So let me take my sine graph, and let's just suppose I wanted to do a center around x equals 2. In other words, I want to create polynomials centered at x equals 2 that approximate my graph around x equals 2. So as I increase the powers, you can see that I have polynomials again, in which the polynomial and the function match at x equals 2 and are close to that in the surrounding area. The higher the degree, the better the match is for a longer interval. So the point is that we can do this approximation process not only around x equals 0 as we did for Maclaurin polynomials, but around any value as long as the function is differentiable there, x equals a. And that's what we're going to work towards. We have our understanding of Maclaurin polynomials, the formula for the polynomial centered at x equals 0. We now want to move towards centering it at x equals a. And this is what we call a Taylor polynomial. Now, I can develop this idea the same way I did with Maclaurin around x equals a, and the formula will be pretty much the same, except that instead of being f of 0, f prime of 0, f double prime of 0, those will be replaced by f of a, f prime of a, and my powers of x will actually be powers of x minus a, x squared, x minus a squared. So really, a Maclaurin polynomial is just a special case of Taylor polynomials. Maclaurin polynomials centered at x equals 0, Taylor polynomials centered at x equals a. So let's find the third degree Taylor polynomial for f of x equals e to the x at x equals 2. Just in terms of visualizing this, I don't want my center to be x equals 0 as you see the polynomials centered here. Those would be Maclaurin polynomials. I want them to be centered at x equals 2. And we want to come up with the third degree equation, which you can see here. This is what we're going to develop through our formula. So let's just write the general third degree Taylor polynomial out just to get used to it. F of a, the first derivative at a, over 1 factorial, x minus a to the first. The second derivative at a, over 2 factorial, x minus a to the second. And the third derivative at a, over 3 factorial, x minus a to the third. My a is 2. Now I also need the derivative of f of x up to the third derivative. Well, I know that all the derivatives, all n derivatives, will be e to the x. So my derivative at first, second, third, and original point at 2 will be e squared. So it's this that I'll be putting into each of these spots, along with a equals 2. So putting that all together, that'll be e squared plus e squared over 1 factorial, e squared times x minus 2, and plus e squared over 2 factorial, x minus 2 squared, and the third derivative of f at 2, again e squared over 3 factorial 6, x minus 2 cubed. And you don't need to multiply this out in decreasing powers of x. We'll just leave these in powers of x minus 2. And there's my Taylor polynomial, which of course you could use this formula to approximate values of e to the x around x equals 2. So if you wanted to approximate e to the 2.3, You could put 2.3 into your formula, and that would give you an approximation for e to the 2.3.